Hello, welcome to Endor Model Railway. After a 6-month break, I've returned to my project to make my own DCC decoders, starting with one that just controls a locomotive's directional lights. At the end of the previous video on this topic, I was a little bit stuck wondering why the decoder I'd built wasn't working. To start with, I was quite determined to work out why it wasn't working, but to be honest, that began to suck the fun out of the project for me, so upon returning to it, I decided to move on and just make another decoder with some slight differences. For context, I'll give another recap of how this decoder works, especially as it's been a while since the last video, and I'll incorporate the component changes I've made. Holes 3 and 4 of a 6-pin DCC decoder socket are connected to track power. Track power is constantly quickly flipping. The direction of current alternates, but the voltage remains constant. When one rail is at 0 volts, the other one is at full positive voltage, 13 volts in the case of my gauge master system. Neither rail ever goes negative. 2 diodes on the bottom of my decoder allow current to flow out to whichever pin is at 0 volts, and 2 on the top allow current to flow in from whichever pin is at 13 volts. These particular diodes drop 0.4 volts. So compared to the 13 volts track power, they create one point on my board that's always at 12.6 volts and one that's always at 0.4 volts. The point at 0.4 volts acts as ground for most of the other components on the board. The brain of my decoder is an ATtiny85 microcontroller, which I need to power with 5 volts in order to run it at 16 MHz. To get a stable 5 volts, I use a voltage regulator. Its input is connected to the 12.6 volts from the decoder's input diodes, and its ground is connected to the decoder's output diodes. The voltage regulator needs external capacitors for input and output voltage stability. To save space, I've got the voltage regulator on the underside of the decoder and the capacitors on the top side. The capacitors are connected in parallel. The 5-volt output of the voltage regulator is connected to Vin on the ATtiny. And, as with the voltage regulator, the Tiny's ground is connected to the decoder's output diodes. Compared to track power, the ATtiny gets 5.4 volts in and its ground is at 0.4 volts. That's a difference of 5 volts, and from the point of view of the ATtiny, it's getting 5 volts input and its ground is at 0 volts. But I'll refer to the values in the context of track voltage. My analysis of my test locomotive, the non-motorised driving cars of a Dapol Super Voyager, revealed their lights get positive voltage directly from the vehicle's circuit board, and the negative of each colour goes back to holes 5 and 6 of the decoder socket. As an aside, that means the decoder can't provide any kind of stay-alive power to prevent the lights from flickering, because it's only got a connection to one end of the circuits for the lights. To switch the red or white lights on, the decoder has to connect pin 5 or 6 back to track, with an extra resistance of 1 kΩ to account for DCC track voltage being higher than DC voltage. My previous attempt used bipolar junction transistors as switches to make or break the circuit for pins 5 and 6. This time around I've used logic-level MOSFET transistors, just in the hope they'd somehow solve the problems I'd been having with the previous decoder. Taking one light colour at a time, the negative end of the red lights are connected to DCC pin 5, which is connected to a 1K resistor. That's connected to the drain pin of a transistor, and the source pin of the transistor is connected to the decoder's ground, which leads back to the DCC track pin that's at 0 volts. The gate pin of the transistor is connected to a general-purpose input-output pin on the ATtiny85 via a 220 ohm resistor. It's possible it would have been okay without a resistor, but from what I've read it's better to have one. When the ATtiny sets that GPIO pin to the ground value of 0.4 volts, the transistor will act like an open switch, preventing current from flowing through the circuit for the red lights. When the GPIO pin is set to 5.4 volts, the transistor will act like a closed switch, allowing current to flow in the red light circuit. The same goes for the white lights on DCC pin 6, with equivalent resistors, transistor and GPIO connection. To monitor the DCC signal, an external interrupt pin on the ATtiny is connected to DCC pin 4, which is one of the DCC track power pins, via a diode and 10K resistor. The ATtiny has internal pull-up resistors that can be activated. I've enabled the one on its interrupt pin, so by default that pin is at 5.4 volts. When the DCC track pin it's connected to goes to 0 volts, current is allowed to flow from the AT-tiny through the external resistor and diode back to the track pin. That will cause its interrupt pin to be at 0.4 volts, like the rest of the ground connections on the decoder, which from the perspective of the AT-tiny will look like 0 volts. When that track pin goes back up to 13 volts, current won't be allowed through the diode, so the AT-tiny interrupt pin won't be connected to anything and will be pulled up to its default of 5.4 volts. The physical layout of this decoder is slightly more compact than my previous one, but it has the same number of components and the logical connections are identical even though I'm using a different type of transistor. The resistor values between the AT-tiny and the transistors are a lot lower. They were 6.8K for the bipolar junction transistors. Construction of the decoder was pretty straightforward. This time I used flux for all solder connections and didn't have any problems with connections breaking after being tested with a multimeter. To start with, I did functional testing using my thrown together decoder tester. I intend to make a better one in the future, but for now this is good enough. Though the red and white lights are connected to the wrong pins, they need to swap around. First, I tested the voltages at various points without the AT-tiny in place, then manually connected the transistors to some voltage to activate them. When those checked out, I plugged in the AT-tiny taken directly from the previous decoder, and it correctly performed the little startup routine of light flashes I programmed it with. Next, I connected it to the DCC system on the layout, where it behaved exactly like the previous decoder. It started up, did its lights flashes, then waited for a command on address 4. When a speed and direction command for address 4 was issued, it responded by illuminating a light. But once a light was on, it stopped responding to change of direction commands. So, no magical fix just from switching to MOSFET transistors. That's a shame. I thought I'd have a bit of a go at some more tests, but they tend to involve a lot of back and forth to my computer to make programming tweaks to the AT-tiny, so I disconnected my DCC system from the railway and set it up on my dining table for easy access. The decoder immediately started working just as it should. Interesting. I transferred the AT-tiny back to the older decoder, which worked fine too. Very interesting. So much for easier access for experiments and taking measurements. The decoders would only misbehave if connected to the railway. That made me wonder about DCC signal distortion through the wiring and connections of my layout. With the DCC system plugged back into the layout, the decoders became even more flaky than before when connected to track, but would work if I connected them directly to the terminals of the DCC base station. I concluded they must be struggling with signal distortion to some extent, and it must be that sometimes the signal is just about clean enough for them to work and act on a command, but with the current for the LEDs running through them, perhaps it was causing enough extra electrical noise to push the distortion beyond what the boards could handle. Commercial decoders I've bought over the years have worked on this layout, so the signal can't be unacceptably bad. My next idea was to replace the internal pull-up resistor on the AT-tiny's interrupt pin with a stronger external one, mainly as just something to try. It's something that's been suggested to me in comments on previous videos, and I did have some success with that. Having reprogrammed the AT-tiny to disable its internal pull-up resistor, I held a resistor in place between its VCC and INT0 pins, and it started to work. I tried a few values of resistance and settled on 10K. Since that worked, I soldered a 10K resistor between those pins on the underside of the decoder, but after that it stopped working. I've seen that capacitors can be used to help stabilize noisy signals, so perhaps my body was providing enough capacitance to do that when I held the external resistor in place. In my code on the AT-tiny, I ignore any change of logic level on int0 that happens too soon after the previous change. Since it was looking like signal noise probably was the issue, I increased the ignore time from 10 microseconds to 40, and with that the new decoder started working. I then programmed another AT-tiny with its internal pull-up resistor enabled and installed it in the older decoder, and that one started working too. I did try variations on this ignore duration in the past, but maybe this time I've stumbled on an optimum value by chance. None of my 4 Voyager driving cars have a complete set of working lights anymore, but I was able to use the decoder to control the white lights on one of them. When I started to suspect signal noise on the layout, I finally decided to buy an oscilloscope. It cost just under £40 and said it takes 10 million measurements per second, which seemed like it should be fast enough. I got the decoders working while the oscilloscope was on its way to me, but it was still interesting to use it to see the DCC signal for the first time. I've measured the signal at the track, directly at the terminals of the DCC station, and just about managed to get a measurement on the decoder with and without a test board LED active. The tricky thing is that I need to hold both points of the probe and then pause the image on the oscilloscope screen, which needs 3 hands really. I haven't spent long working out how to adjust the oscilloscope properly yet, but it looks like the DCC signal is generally fine. There's clearly some noise at the corners of the square waves, and it seems like the voltage doesn't necessarily stay completely consistent in between changes, but I'd say it's very clear here where the changes are and how long each state lasts. If there are significant fluctuations, then they must be too brief for 10 million measurements per second to detect. For a DCC 1-bit, for example, which should be between 52 and 64 microseconds, 10 microseconds from when it changed would be somewhere around here, and there's clearly nothing odd going on after that. The signal is either very clearly high or very clearly low. I'm sure the oscilloscope is going to be a very useful tool in the future though, and doesn't take much space to store. I'm very pleased these decoders are now working properly, and there are several next steps I can consider taking with the project. I've already got code somewhere that respects whether or not the vehicle lights should be on or off, as well as in which direction. I need to find that and reinstate it. That'll be easy. When I originally decided to use the Tiny 85s for decoders, I intended to use a physically smaller version, and I've got some boards to solder them onto. Those will save a lot of vertical space compared with the socket and larger format that I've been using while working through problems. With that in mind, I also need to see if I can still program these whilst they're electrically connected to the other things on the board, because it won't be easy to remove and reattach them once they're soldered on. It would also be good to enable these decoders to have their DCC address set by the DCC system. For the most basic implementation, I don't think I'll need any hardware changes to achieve that, because two-way communication is optional. I think I can achieve it just through code changes. That's all for now though. Bye bye.